Okay, so here we are with the second part of this vector notes. So tail to tip rule for vector addition. What we're going to do there is we're going to translate, okay, so that the tail of vector v is located at the tip of vector u. All right, so what that looks like here is if we have vector u, let's say we have vector u defined as 4, 1, and let's say we have vector v defined as 1, 3. If I were to draw those two vectors, vector u would be here. Okay, and that would be vector u. And then let's just say vector v then is 1, 3. Okay, and that's vector v. If I want to add them together, what I want to do is I want to grab vector v. Oops. Okay, I want to grab vector v and slide it, translate it so that the tail end lines up with the tip of vector u. Okay, and then the resultant vector, okay, would be what I get when I start at the tail of the original vector u, okay, and go all the way to the tip of vector v. This would be u plus v. Okay, now for now, we're only adding these vectors in component form. Okay, so if I was going to add vector u plus vector v, okay, I would be adding their components or their like parts. All right, so u plus v would end up being 5, 4. All right, so basically I'm taking this here and turning it into an addition problem. All right, x components get added together for 5, y components get added together for 4. All right, and that becomes my new vector, u plus v, the resultant vector. Okay, similar idea if I subtract the vectors. Remember, in reality, there's no subtraction, right? We're just adding the opposite of the vector that we have. Okay, if we would do u minus v. Okay. So we would just have to go in the opposite direction, okay, for whatever vector is being subtracted. All right, so if I rewind here, my vector u is 4, 1, okay. All right, if I was adding vector v to it, okay, then again I would draw vector v and I would slide vector v, okay, but I'm not really adding v per se here because remember that I'm going the opposite direction, okay, for vector v. So instead of 1, 3, okay, I would be going -1, -3, okay, if I was subtracting that vector v, okay. So it's going to get a little confusing to think about here. So 1, 3, oops. Okay, that's vector v. But again, if I really want to subtract them, then I would be doing the opposite of that. Okay, and then I would slide so on, so forth. So the opposite of vector v, because I'm subtracting it, right, would be -1, -3. All right, so it would actually look like this, right? Same vector, opposite direction. Again, same idea though. I'm just taking that, turn into addition problem. So I'm going to slide the opposite of vector v over to the tip of vector u. All right, and then I'm going to draw the original from the tail of u to the tip of v. All right, and that would be u minus v. All right, so basically I had vector v, okay, here, and this is actually negative v, okay, so it's still vector v, just in the opposite direction. Then I would have u minus v. And when we're in component form, same idea, we're still just subtracting them. So 4 minus 1, okay, and 1 minus 3. So that means that my resultant vector for u minus v, okay, should equal 3, negative 2, okay, because I'm just subtracting the components. All right, so let's practice some of that here with some examples. So find 2v plus w. So I'm using, again, I'm using the vectors up here that they give me for v and w. All right, so 2v, okay, so 2 times vector v. That's scalar multiplication. I think you guys did that in the last video. All right, plus vector w, which is 2 comma 4. So do your scalar multiplication first and then add your vectors together. All right, so that would give me negative 6 comma 10. And I'd be adding that to 2 comma 4. All right, and I will get my resultant vector there would be negative 4 comma 14. Okay, so my best answer. All right, over here, w minus v. Okay, same idea, so I have vector w, which is 2, 4. I'm subtracting vector v, which is negative 3, 5. Okay. In doing so, right, I would be subtracting, so I'd give the opposite here and the opposite there. All right, so my resultant vector would be 5 comma negative 1. All right, that's the answer there. Okay, unit vectors would be vectors that have the same direction, okay, with a magnitude of 1. All right, so we would like the magnitude to be 1 here. Okay, so the way that we get that, okay, is by finding the magnitude and dividing by whatever that particular number is of the vector. Okay, so we use the components, okay, to find the magnitude of the vector, and then we divide each component by the magnitude, okay, to get our answer. Okay, so if I see that in practice here, find a unit vector that has the same direction as vector v, which is 3i minus 4j. So the magnitude for 3i minus 4j, I'm just doing Pythagorean theorem there, 3 squared plus 4 squared equals c squared. That's a 3, 4, 5 triangle, so the magnitude here is 5. Okay, so the magnitude of vector v, okay, is 5. Therefore, the unit vector would be 3/5, okay, and negative 4/5. All right. And if I was to find the magnitude of this new vector here, the unit vector, it would be 1. Okay, so if I were to find the magnitude here, and that was our goal, if I would find the magnitude here, right, I would get 3/5. Okay, and that's sort of a quick check. All right, plus 4/5 squared. Okay, and that's actually going to give me 1. So good job. Okay. Equal vectors. Let's talk about what equal vectors means. Okay, same direction and same magnitude. Okay. So 2 vectors that have the same direction. Okay. I'll make that easy. Okay, there you go. All right, so they have the same direction, okay, and the same magnitude. All right, and it really wouldn't matter where I translate this second one to, okay? I can move it anywhere, here, 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 here. As long as it's the same magnitude, same direction, okay? They are equal vectors, okay? So we're looking for parallel, all right, and equal magnitudes. Same magnitude, opposite direction. These are not necessarily equal vectors, okay? Because they go a different direction, right? So one vector could be going this direction. Oops. All right, and the other vector could have the same length, okay, as the original, but be going a different direction. All right, same magnitude only. All right. So we would have 2 vectors with the same magnitude, all right, going completely different directions. All right, and then if they have different magnitudes, obviously, then, all right, they could be going the same direction, but different magnitudes, okay? All right, so direction angle of a vector, and this is something that we should already be equipped for since we have been working with right triangle trig for a little bit, okay? And that is to find the direction angle. All right, now they give you these big fancy formulas here. I don't know that that's really something that we need. We've already talked at a great length, about, cosine B related to X, sine B related to Y, and so on and so forth. But the positive angle between the x-axis and the position of the vector is going to be what we consider the direction vector, or the direction of the vector, right? So if I have vector AB, okay, so right here is vector AB. All right, A, B. This angle right here is what I would call the direction of the vector, okay? All right, keep in mind this would be the magnitude of the vector, okay? And the way that I'm going to find that, okay, is by basically making a slope triangle, right? So I'm going to do this, and I'm going to do this. I know what A is, I know what B is, so which of my trig functions associates the adjacent side to the opposite side, and that would be tangent, right? So tangent of theta is going to be opposite over adjacent, B over A, in this particular case, okay? So let's take a look at what that looks like. So find the direction of vector V if vector V is defined as negative 2, comma 5. So negative 2 and 1, 2, 3, 4, 5. Draw that up here. There you go. Okay, so I know that, okay, this side is 5. I know that this side is 2. Okay, I'm looking for this vector, or this angle right here. Okay. Now, to find that angle, right, I'm going to find this little angle first. Okay, I'm going to use my knowledge here of my coordinate plane, knowing that that's 180 degrees, okay, to determine what that angle is. So, tangent of theta equals opposite 5 over adjacent, okay, 2. And I'm going to go ahead and do the inverse tangent there to get that angle measure. All right, so make sure I'm in degrees. And what do I got here? 5 over 2. All right, second tangent. So 68, right? I get 68 degrees, okay? So from 180 though, right, because I want this, it's always the positive x-axis, okay, and the vector is what the angle or the direction of the vector would be, right? Okay, so I'm going to do 180 minus 68, and that's going to give me 112 degrees. Okay, so the direction of this vector would be 112 degrees. All right. Okay, so we'll see here. How much more do we got? Yeah, we'll do this last problem here. All right, so find a vector whose magnitude is 6 and is in the direction of negative 3, comma 3. Okay, so first here, what we want to do is determine what that direction is. Okay, so I would have inverse tangent here. Okay, so theta is going to be the inverse tangent of, all right, 3 over negative 3. All right, so I'm going to get 135 degrees for that. Okay. And I would like the vector to have a magnitude of 6, okay, and it's going in that direction, okay. So what I'm going to do here then is I'm going to I'm going to draw my picture here real quick, okay. Remember that that's the 135. So I know that this is 6, okay. I am looking for the two component vectors that make this up, right? This is not drawn to scale. So I'm looking for the x component, all right, and I'm looking for the y component, okay? So this just comes down to some general knowledge of right triangle trig, okay? And I know the hypotenuse, okay? So to find the x components, all right, I'll do that one in purple. All right, so the x component is going to be my magnitude of my hypotenuse multiplied by the cosine of 135. Okay, now if I want this as an exact value, which in this case, since 135 is a special triangle, I can do that. All right, so that would give me x here would be 6 times negative root 2 over 2. So my x component is going to be negative 3 root 2. Okay, and then my y component would be found very similarly. Okay, so my y component is going to be 6 times the sine of 135. All right, so y is going to be 6 times positive root 2 over 2. So y component here is going to be 3 root 2. Okay, so my vector itself would be negative 3 root 2 comma 3 root 2. Okay, I also could have obviously used decimals for that as well. Okay, now if I was writing it in component form, I would say negative 3 root 2i, right, plus 3 root 2j, I think is how they have it pictured here. All right.